So we are going to discuss the illustration of the modeling here. Let's consider a system that, as you can see in this slide. So let's consider a system with a mass. So I have a mass here as indicated by m there. So I have a mass with a mass of m, and then the mass is supported to the ground through spring k with a spring constant of k and a damper element with a damping coefficient of b. So I have mass supported by spring and damper, and then it is supported to the ground. And then imagine if I disturb this mass. So I applied a force to this mass. What will happen? Let's say if I apply force to the mass in the downward direction, what will happen to the mass? This mass will move down by, let's say, x. Okay. So in this system then, to this system that comprises mass, spring and damper, Ft is the force applied to the system. So Ft, the force Ft is the input to the system, and as a consequence the mass will be displaced by x. So x, the displacement of x, is the output of our system. Okay, we are now going to model the relationship between input f and the output x of the system. So to have a better illustration on this system, you can take a look on the animation of this system. Now we are going to derive the mathematical model of that system to correlate the input f and the output x. Few assumptions have to be taken first. The first one, of course, you need to know the mass, the spring constant, and the damper, the constant, the damping coefficient. You need to know all of this value, m, k, and b. The second one, we take an assumption that the spring satisfy the Hooke's law. What is Hooke's law? The Hooke's law is the property of the spring that say that the force acting on the spring is proportional to the relative deformation. And the last assumption that we take is that we have a damper where the force of the damper is proportional to the velocity. The last two properties that we have already discussed in the previous few slides. Once we have already taken this assumption, we can derive the mathematical model of this mechanical system. So we are going to derive the model now. As you can see in the upper right corner of this slide, we have the model again. I redraw the model, the system again there. So we have a mass supported to the ground through a spring K and a damper B, and then we give a force input to the system. As a consequence, the mass will be displaced by x. So x is the output in this case. We are going to find the relationship between input f and output x. So how to do that? First, I will redraw the mass separately. So this is the mass. What will happen to the mass? I'll give a force input to this mass. As what we have discussed, as a consequence, the mass will be displaced by x. So x is the output here. I take an assumption when I apply a force in downward direction, the mass will be displaced also to the downward direction by x. Now let's take a look on the spring. If the mass is moving down, what will happen to the spring? The spring is stretched, isn't it? Because the upper end of the spring, as you can see in this drawing, is fixed to the ground. So when the mass is moving down, the spring is stretched. If the spring is stretched by x, because the mass is moving down by x, of course the spring is also stretched by x, what will happen to the spring? There is a force acting in the outward direction, where the force here, the internal force of the spring, is proportional to the relative deformation. The spring is stretched by x. So to the spring, there is a internal force in the outward direction, which is equal to k times x. What happened to the mass? It's similar to what I feel in my hand when I stretch a spring. When the spring is stretched, the mass will receive a reaction force. You can imagine the mass as your hand. So when your hand is stretching the spring, you will feel that the spring is trying to pull you back to the upward direction with the same force. To that mass, there is a force from the reaction of the spring, where the force is equal to the force acting on the spring, but the direction will be in the opposite direction. To the mass, there will be a force to the upward direction, where the force is equal to k times x, right? Which is, this force is the reaction force from the spring. Now, if you take a look on the damper, it's also the same. The mass is moving down with the speed of x dot. So this is moving down with the speed of x dot. That means to the damper, there is a applied force which is proportional to the rate of deformation, b times x dot. But this is the force that is applied to the damper b. As a consequence, the mass will receive the reaction force. The reaction force from the lower end of the damper. The direction will be the opposite of this force. So on the mass, you will have an additional force in the upward direction, where the force is proportional to the rate of deformation x dot, which is equal to b times x dot. So we have already drawn all of the forces acting on the mass. The input force Ft, the reaction force from the spring Kx, and the reaction force from the damper Bx dot. The mass is moving down by x. And then now we can apply the Newton's second law. Newton's second law, you still remember? Newton's second law says the total forces acting on the mass will be equal to the mass times the acceleration. Acceleration is x double dot, if x is the displacement. So I take the direction of mx double dot in the downward direction, following the assumption of the displacement that we took before. So in this case, then downward direction will be a positive direction. So next, I can apply the Newton's second law. Total force acting on the mass is equal to, again, as I mentioned, downward direction is positive, so Ft is positive, minus Kx, because Kx is pointing upward, minus Bx dot. This is the total forces acting on the mass. And as Newton said, the total forces acting on the mass will be equal to the mass times acceleration. Okay. So the model is more or less finished here. Now I just have to manipulate this mathematical equation. So I group x with x and f in the other side. So I rewrite the equation. Now it's becoming mx double dot plus bx dot plus kx is equal to f. Again, f is the input and x is the output in our system here. So in this case, we have already derived the mathematical model of the system in the form of differential equation here. Of course, in our case here is ft is there is no force acting on the system. What you will have is the displacement because of the initial condition. But this is something else. I will not discuss this in more detail. I just want to illustrate to you on how to derive the mathematical model of mechanical system. So at this point, we have already derived the model here of our system, where the relationship between input f and output x is represented by this differential equation. We have already derived the mathematical model of the mass spring damper in the previous slides. We just discussed it. And then we derive the model in the form of differential equation. You still remember in the previous topics last week, we discussed that there are at least 3 different modeling approaches. You can represent the model in the form of differential equation. You can represent it in the form of transfer function. And then the last one, you can also represent it in the form of block diagram. You just need to know one of them, and then you should be able to convert it to another type, another form of modeling. So since we have already derived the model in a form of differential equation, you should be able also to convert it to another form. Let's try to convert this model, the mass spring damper model, which we have in differential equation form, to transfer function form. We discussed that before. If you want to convert the differential equation form to transfer function form, what we have to do, you have to Laplace transform it first. That is the first step. So I will Laplace transform the differential equation there. The input ft, I will transform it to Laplace domain. It becomes fs. The output x, I will, in time domain, we can transform it to Laplace domain. It's becoming capital XS. So the third term in the differential equation form of this model, kx will become k times capital XS. The second term, bx dot, we just simply use the differential properties of Laplace transformation. If capital X is the Laplace of x, so if the Laplace of x is equal to capital XS, as what we have already discussed from the differential property of Laplace transformation, the Laplace of the first derivative of xt will be equal to this term. So this terms is the Laplace of bx dot. The first term, mx double dot, we use the same property also, the differential property. And the Laplace of x double dot, if you refer to the differentiation property, the Laplace of x double dot will be equal to this term. So this last term is the Laplace of mx double dot. So we have already Laplace transform all of the terms in the differential equation. The next step, if you want to convert the differential equation model to the transfer function model, you have to assume all of the initial conditions are equal to 0. So this is the first initial condition. We set it to 0. This is also the second initial condition. This is the last one. We set all of the initial condition to be 0. So what we have now is only Fs, Kx, Bsx, and Ms square x. If you do mathematical manipulation, then you can rewrite that equation into this form. Again, transfer function is the ratio between output and input in Laplace domain. Input is f, the output is x, so the ratio between x and f in Laplace domain will be equal to this one. We have already discussed one simple example of deriving model of translational system. This slide will give an illustration on how to derive a mathematical model of rotational system. It's pretty similar like what we did before for a translational system. So if you refer to the drawing on the right side of this slide, you will see there is a disk with a moment of inertia of J. We have a disk here. The disk is supported to the ground with a flexible shaft with a spring constant of K, and then it is also supported by a damper element with a damping coefficient of B. The disk is then excited. To the disk we give a torque input which is equal to tau A in a clockwise direction. Consequently, of course, the disk will rotate also in the clockwise direction by the angular displacement of theta. Now we are going to derive the mathematical model of this system, where the input is tau A, the torque, and the output is theta, the angular displacement of the disk. So how to do that? It's similar to what we did to a translational system. We analyze element by element. We started from the spring. We have spring here, rotational spring. The right end of this spring, the shaft, is connected to the disk. Since the disk will rotate in the clockwise direction by theta, so the right end of this shaft will also rotate to the clockwise direction by theta. Imagine you have shaft, you twist it in a clockwise direction on the right end, and you keep the left end fixed. What does it mean? This means you are applying a torque in this direction as well, in the clockwise direction at the right end, and to the counterclockwise direction at the left end. So you squeeze it like that, where the applied torque here is proportional to the relative angular deformation, which is K times theta. This is the torque applied to the shaft, the torque applied to the spring, to the rotational spring. So what will happen to your disk? To the disk, we applied the input torque tau A, and then to the same disk, there will be a reaction torque coming from the spring, coming from the shaft, from the right end of the shaft. The torque because of the shaft, of course, will be the same, will be equal to K theta, but the direction will be the opposite. Why? Because of the reaction of the torque. So to this disk, there will be a reaction torque from the shaft, where the torque is also equal to K times theta. Okay, but then you have the other element on the system, which is the damper. The property of the damper is similar, again, is similar to the spring. The only difference is that the torque of the coming from the damper is proportional to the rate of deformation. Direction wise will be similar to the spring. So to this disc, then you will have another torque with the same direction like k theta, but the torque will be equal to b times theta dot. So we have three torques applied on the disc: tau A, k theta, and b theta dot. We can apply now the Newton's second law. Newton's second law says that the total torque will be equal to the inertial torque, which is equal to J times theta double dot. The direction will be clockwise because the direction will follow the direction of the displacement theta. So we just sum all of the torques applied to the disc. Clockwise is positive because it will follow the direction of the deformation, the direction of the inertial torque. So in this case, tau A is positive, k theta is negative, b theta dot is also negative because it is in a counterclockwise direction. The total torque, this will be equal to j theta double dot. And then from here, I just simply manipulate this equation mathematically. J theta double dot plus b theta dot plus k theta will be equal to tau A. So this is the differential equation that relates the input tau A and the output displacement theta. This is how we come up to this model. Once you have the model in differential equation, same like in the previous example, you can always be able to convert it to transfer function form by applying Laplace transform to the differential equation and then take all the initial condition equal to 0. After that, you take the ratio between the output theta and the input torque tau A in Laplace domain. Then you will have the model in transfer function form like what you see in this equation. These last two slides illustrates us how to derive the mathematical model of mechanical system.